Hello guys, today we're going to talk about mass transfer, but we're going to start with the principal things about mass transfer. The idea of this one is that, as we already checked, is the situation that we have the relation of the pressure, how it works, and what are the deals that happens in here. What happened in this situation when I have the pressure, the concentration, and the distance that we're referring. The idea of the mass transfer is when we get to the equilibrium, okay? We have to get all the things similar. Remember that all the things in the environment, in the nature, in everything have to be the same. For example, if I have in here 1, in the other part I need to have 1. So they have in the equilibrium. So they tend to the equilibrium. So the idea of this one is that I have a system where the pressure is given by one and the pressure is given by another thing. We have two pressures or two concentrations, but when they start moving around, they are going to get in the equilibrium. So in this one I have 2 and in this one I have 1. This one is going to get in this situation and this 2 is going to get in this. So I will have 1 and 0.5 and 1 and 0.5. So I have the equilibrium, the perfect equilibrium of the situation. That's the principal situation. That's the idea. What happens? Well, we have to consider the distance. The distance is one of the most important things that we're going to refer in this part. The distance that is going to move around. So if I have a pressure in the part 1 and if I have a pressure of a component B in a part 2, they're going to move to the part 1 and they're going to move to the part 2 according to the position. When they move, the movement we have to consider it. Maybe it's going to take some time to move around, so we have to get that situation on mind. Okay, so be careful. In that case, you have to take in account the distance. Well, then the principal equation that we have in this case is this one. Well, the principal equation is this one. To be clear, the difference of the concentration and the difference of the distance. But we're going to transform this one. How? The concentration can be given by this one, by the volume that is referring to what? To the mole, to the concentration is referred as the number of moles, and the volume. This one is going to be referred as a pressure that is divided by a constant of gases and the temperature. So if we get these two together, we're going to get that we have a difference of pressures and the constant of gases and the temperature. So if I have this situation, I will consider the diffusivity and I will consider the distance. Okay, we're going to have the pressures and we're going to have the distance. So it's going to leave us the equation that we have in here. The pressure that is referring to what is happening. Now, we're going to get a problem. We're going to solve a problem. Maybe you remember it. But this problem is what? Well, air and dioxide are mixed. Air at 3 atmospheres and 30 Celsius degrees enter to one end at a rate of 2 kilomole per minute, and the dioxide enters in the same conditions, but the rate is different. It's going to be 4 kilomole per minute. The two gases pass through a pipe. Well, the first thing that they are asking is to calculate the dioxide that is entering. Well, in this point, we're going to use the equation, the first thing that we have to consider, that we don't have a concentration, so we're going to have a relation of the pressures. So how do I consider this? Well, the dioxide that we have, the dioxide is entering at a 3 atmosphere pressure, right? And then the constant of gases. Well, the constant of gases, they are in a different situation. We can have different constants. The first situation that we're going to consider is that we have a constant that is 0.082057. We're going to get why we have that situation. The temperature that we have is working in 30 degrees, but the constant of gases, they have some units that they are atmospheres, kilogram, and also they have kilomole. In this one is cubic meter and Kelvin degrees. So if I have Kelvin, I have to transform the 30 degrees Celsius degrees to Kelvin. So to transform this, I have to add this situation, and I'm going to transform it. So I'm going to obtain 303.15. In this situation, I will have the same units. So I have atmospheres, atmosphere, cubic meter, kilomole, and Kelvin. And in this case, I have Kelvin. I'm going to eliminate the atmospheres, and we're going to obtain, at the end, we're going to obtain atmosphere, kilomole, atmosphere, cubic meter, atmosphere, we'll leave it, and we're going to obtain one data. This data, the units are going to be kilomole per cubic meter. The result of this operation is going to be 0.121 kilomole cubic meter. Well, but they are asking that my result has to be in kilogram per cubic meter. To transform this, remember that, pay attention to this situation. I have 1 mole of the oxide is going to be 44 grams. This one is going to be the same as if I consider 1 kilomole of the oxide is going to be the same as 44 kilograms. Okay, it's totally the same. We're going to consider it as the same situation. Then, having this in mind, I will put 1 kilomole is the same as 44 kilogram. If I multiply these two, I'm going to obtain 5.31 kilogram per cubic meter. And that's the first result. That's the amount of the oxide that it's entering. Now, let's go with the second part. The second thing that they are asking about the nitrogen that is entering. Well, to consider the nitrogen is something that is given by what? Well, I don't have as seed the nitrogen. I have one consideration that it's called air. The air has 79% of nitrogen and 21% of oxygen. So, as it, I will have in the air, I will have 79%. This one we can consider as a fraction, but it is expressed in a percentage. So we're going to transform. If I want to consider it as a fraction, I have 0.79 of nitrogen and 0.21 of oxygen. Having this in mind, we're going to get to the same deal using a simple equation. The equation that we're going to get is the pressure, but now we're going to work with a fraction this is the fraction of the particle. We can call it, we're going to call it that way. We're going to have the fraction. This fraction, we already know it. If we want to consider the nitrogen, okay, I will put 0.79. But if I want to work with the oxygen, I will put 0.21. In this first part, I want to work with the nitrogen. And I have to consider the total pressure. The total pressure of the system is given by what? Of the air is 3 atmospheres. So I'm going to work 3 atmospheres. This operation is going to leave a result of 2.37 atmospheres. Well, now we already have the pressure. This pressure is the one that we're going to use in the equation that we already checked. The equation that it's, I already have the pressure that it's 2.37 atmospheres. Well, the constant, well, they are asking now in pound mole cubic feet. Well, we can use different constant of gases. Okay, in this one we're going to use another one. Remember, we have different constants. Okay, this one is given by this amount, but the units are different. The other ones were kilograms. In this one are going to be feet, cubic feet, pound, mole, and the Rankine. Now, the Rankine degrees are different. So, to calculate the Rankine degrees are going to be what? We're going to multiply 1.8 by the Kelvin degrees. So, I have to transform 30 degrees to Kelvin and then to the Rankine. So, considering this, 1.8 is going to multiply 303.15 Kelvin degrees. In this situation, I'm going to obtain the Rankine that is given by 545 Rankine degrees. Well, I already have the degrees, 545 Rankine. In this case, I'm going to obtain the units that they are asking, pound mole. Well, the result of this is going to be given by, the multiplication of this is going to give a result of 5.95 to the minus 3 pound mole cubic feet. Okay, that's a situation when I'm considering the two parts. Now, the part 3 is in a certain way different. Okay, why different? Well, the different situation is that they are talking about the dioxide that it's leaving. So if I consider the system, in one part is entering the air, in the other is entering the dioxide. When they mix, in this part, the consideration that the flux that they are entering is going to be different. Okay, we're not going to consider it 2 or 4. We're going to consider it as a mix. So, according to a mix, we have to mix it. So, we're going to consider the first part, that it's the dioxide. The dioxide that it's entering is what? The rate of dioxide is 4. If I go with the oxygen, And if I go with the nitrogen, well, first of all, consider the air. The air is 2, right? So if I consider this situation, I'm going to divide the air in oxygen and nitrogen. The oxygen is going to be given by 0.21 and the nitrogen by 0.79. This one is the same as if I multiply this. I'm multiplying the rate of entering. So the first one I considered 4. The second one of the oxygen I will consider 0.42, and in the third one, the nitrogen, I will consider 1.58. The adding of these two is going to be 2. So I'm not affecting the situation. The total of mass is 6. In this case, I will know what's the rate, what's the living rate, the output rate. The output rate that I have is that the dioxide is giving me 0.667. The nitrogen is giving me 0.07, and the nitrogen is giving me 0.263. Well, these values are going to be the ones that I'm going to use. How? When I consider the pressure, the new pressure. Well, sorry, yes, when I consider the new pressure. The new pressure that I have is this one. The dioxide that I have is going to be given by what? Well, the pressure that I have and the fraction. What's the fraction that I have now? 0.667. That's the new fraction. So if I multiply this, I'm going to obtain the living condition. I'm going to obtain the pressure in a living condition. This value is the same as in this one is given by 2. So I consider now that the pressure that I'm going to use is going to be 2, and it's going to be divided, as I already told you, that we have different constants. They are now asking me mole and the cubic centimeters. So I'm going to consider the next one, that is going to be, this is a new constant, okay? A new constant of gases. And the temperature is the same. If I consider those amounts, what happens? My result is going to be given by what? Well, first of all, the units are going to be atmosphere, cubic centimeter, and mole, Kelvin degrees. When I do this, I'm going to obtain the first thing, my first result, that is going to be 8.04 to the minus 3 mole cubic centimeter. Okay, that's the first result that I'm going to obtain. 8.04. Well, that's the part number 3. And the part number 4 we're going to obtain. Now we're going to consider the oxygen. The oxygen, check this. We're doing a big difference, no? The oxygen, the amount of the fraction of oxygen is different. It's not going to be 2. The amount of oxygen is going to be given by what? Well, the pressure is going to be what? The same pressure, but the fraction of oxygen was 0.07. So this result as a 0.21. This 0.21 is the one that we're going to substitute in here, giving us what? The result, well, this one is going to give us the 0.07, and in this one the 0.21, and in this one the 0.21. We're going to change again our constant of gases. Now we're going to use the new constant, but now this new constant we're going to put it in the terms that we need. What terms we need? Well, we can work in different things. Let's think about the first constant that we used. The first constant that we used was 0.082057. That was the first constant, and the units were atmosphere, cubic meter, kilomole, and Kelvin. Well, knowing this, we can do the operation, and it's going to be simple. We're going to obtain the result for the part 2. Well, for the part 4, no? And we're going to obtain the result that is going to be 8.44 to the minus 3 kilomole cubic meter. And that's the way we answer the first exercise. Well, that's the first thing, that's the first condition. What are you going to do? Well, you're going to do something simple. You're going to answer this exercise by yourself. How? We're going to change what? We're going to change the pressures. We're going to change the temperatures. And we're going to change the rates. The rates now are going to be in these conditions, and we're going to consider the nitrogen leaving, okay? But this nitrogen that is going to leave, you're going to consider it in pound cubic feet, okay? And that's the exercise that you're going to answer, okay? When you finish, you're going to send me your paper to the email, okay? That's the work that you have for today. Thank you, and if you have any doubt, please contact me and we can solve it.